Hi, my name is Matthew Burns, and I'm presenting my slides on TCP. An introduction to TCP. TCP stands for Transmission Control Protocol and was specifically designed to provide a reliable stream over an unreliable internet. An internetwork differs from a single network because different parts may have widely different topologies, bandwidths, delays, packet sizes, and other parameters. TCP was designed to dynamically adapt to properties of the internetwork and to be robust in the face of many kinds of failure. This slide is talking about the TCP service model. TCP service is obtained by both the sender and the receiver, creating endpoints called sockets. Each socket has a socket number or a socket address, consisting of the IP address of the host and a 16-bit number local to that host called a port. A port is the TCP name for a TSAP. For a TCP service to be obtained, a connection must be explicitly established between a socket on one machine and a socket on another machine. A socket may be used for multiple connections at the same time. In other words, two or more connections may terminate at the same socket. Connections are identified by the socket identifiers at both ends, that is, socket 1 and socket 2. No virtual circuit numbers on or any other identifiers are used. This slide is about TCP connections. All TCP connections are full duplex and point-to-point. Full duplex means that traffic can go in both directions at the same time. Point-to-point means that each connection has exactly two endpoints. TCP does not support multicasting or broadcasting. A TCP connection is a byte stream, not a message stream. Message boundaries are not preserved end to end. For example, if the sending process does 4 512 byte writes to a TCP stream, these data chunks may be delivered to the receiving process as 4 512 byte chunks, 2 1024 byte chunks, or 1 2048 byte chunk, or in some other way. There is no way for the receiver to detect the units in which the data was written, no matter how hard it tries. This slide is about TCP protocol. A key feature of TCP and one that dominates the protocol design is that every byte on a TCP connection has its own 32-bit sequence number. When the internet began, the lines between routers were mostly 56 kilobyte per second leased lines. So a host blasting away at full speed took over 1 week to cycle through the sequence numbers. At modern network speeds, the sequence numbers may be consumed at an alarming rate. Separate 32-bit sequence numbers are carried on packets for the sliding window position in one direction and for acknowledgments in the reverse direction. The sending and receiving TCP entities exchange data in the form of segments. A TCP segment consists of a fixed 20-byte header plus an optional part, followed by 0 or more data bytes. The TCP software decides how big segments should be. It can accumulate data from several writes in one segment, or it can split data from one write over multiple segments. And finally, TCP segments. Two limits restrict the segment size. First, each segment, including the TCP header, must fit in the 65,515 byte IP payload. Second, each link has an MTU, or maximum transfer unit. Each segment must fit in the MTU at the sender and receiver so that it can be sent and received in a single unfragmented packet. In practice, the MTU is generally 1,500 bytes, the Ethernet payload size, and thus defines the upper bound on segment size. However, it is still possible for IP packets carrying TCP segments to be fragmented when passing over a network path for which some link has a small MTU. If this happens, it degrades performance and causes other problems. Instead, modern TCP implementations reform path MTU discovery by using the technique outlined in RFC 1191. This technique uses the ICMP error messages to find the smallest MTU for any link on the path. TCP then adjusts the segment size downwards to avoid fragmentation. And my question is, what are the two limits that restrict the segment size in TCP? And thank you, that is all my slides.